Hi everyone, and welcome to our live solve. We are very, very happy to be collaborating with Math Kangaroo again. I'm sorry I can't quite be in it because I'm actually in Boston right now. In fact, I'm even giving another talk right this minute. However, we want to say that the Math Kangaroo organization has been an incredible organization to work with, in part because they have great questions, and then also in part because they have great people. We're very happy to be joined today by one of their representatives. I'd like to let the representative come in and say a few words, and after that, then our incredible stars are going to take over and do this live solve. So without further ado, I'd like to invite the representative from Math Kangaroo to say a few words.
Awesome. I'm really delighted to introduce Mr. Ravi Karanjakar, who is an engineering major at Amazon. He exemplifies the perfect blend of professional excellence and community dedication. As the California State Director for Math Kangaroo, he has been instrumental in fostering mathematical thinking among young minds through innovative gamified teaching approaches. Beyond his corporate role, Mr. Karanjakar's passion for education extends to running a nonprofit school that helps students maintain strong connections with their cultural heritage and mother tongue. His unique teaching methodology, which progressively builds from fundamental concepts to advanced problem solving, has inspired countless students in their STEM journey. Mr. Karanjakar is currently expanding the Math Kangaroo competition program while continuing his role as an official faculty member. Please join me in welcoming Mr. Karanjakar, who is a true advocate for educational excellence and cultural preservation. Hi, welcome today, Mr. Karanjakar.
Hey, thank you, Sam. Thanks for the warm welcome. Uh, how many attendees are there? It's 100 plus. So maybe let me get started with what we do at the Math Kangaroo side. And I'm sure the audience is already excited to see the live demo, which Eli as well as Sam would be doing, solving the questions live in front of you. So I'm hoping you'll learn a lot of good things today. First of all, I would like to congratulate all the participants who are part of the 2025 Math Kangaroo competition. I'm really excited to see you guys' enthusiasm because exam just happened 2 weeks back and you guys are still here to learn more. So kudos to your hard work and your enthusiasm to get it further. We will soon be announcing the results on May 1st and between those 2-3 days because there are multiple grades. And within next 15 days after that, we will have the state winners as well as the country winners. So stay tuned for that. We also looking forward for your participation in 2026 competition, which will be happening on 19th March next year. Yeah, 19th March. So start preparing. I'm hoping you guys will do much better than this year, as well as you'll be advancing one grade further. So for some people, it will be getting easier competition, whereas some of you, it will be getting tougher. So I wish all you best. Start preparing and do well. I would like to give some more history about what we have been doing at Math Kangaroo. In fact, Math Kangaroo competition started in 1980. That was even before I was born. So I will leave it to you to guess when I was born and what's my age, but it started in Australia. Then we extended to France in 1991, then throughout the Europe, and we started in US in 1998 in Chicago. Since then, it has been ongoing. 2020 was a special year for us. And that's mainly because we were hit by the COVID and we were wondering, oh, how we would conduct this exam because earlier it used to be in person, paper based, and all that. So 2020 is what made us go online, and uh, we were really fascinated to see more than 35,000 people or 35,000 students participated in this online examination, which was great success. So since then, we have been going up and up and up. We see more than 20% growth every year. Recently, the exam which we happened, we conducted in March, around 55,000 students participated in US, which was great. And we are looking forward for your more participation. Ask your friends. Also, reach out to your schools. In fact, this year we started letting schools enter their own nominations. So that registration process is already in progress. So reach out to your schools if they're not participating, and they will be able to register themselves. And we are looking forward for your great success in mathematics. With that, I would like to congratulate you all once again, and stay tuned for more information. I'm looking forward in rest of the session. Eli as well as Sam would be walking you through some of the questions from 2019. They both are sitting in Connecticut and Georgia and still trying to help the students all over the US. So I look forward for their help and learn quite a few great things today. So wish you all the best, and I would let Eli and Sam take it further. Thank you very much.
Yeah, thank you so much, Mr. Kranjkar, for that awesome explanation of everything that Math Kangaroo is. And so now I think I'll go and introduce the person that's down over here. So Sam Covey is a two-time Amy qualifier and placed top 5 at the Georgia State Math Counts competition. And outside of math, she enjoys debate, reading books, and listening to classic rock. So everyone welcome Sam down below, or to my right.
Hi everyone, really excited to be here and thank you all so much for joining. I'm gonna go ahead and introduce my awesome co-TA, Eli. So Eli is a 3-time American Invitational Mathematics Examination qualifier and a USA Mathematical Talent Search perfect scorer. In his free time, he loves Rubik's cubing, playing ping pong, tap dancing, and playing chess. So lots of interest, and we're really excited to have Eli here with us today.
Yeah, thank you so much, Sam, for that introduction. And with all that being said, I think maybe it's time to get started on our first problem. So we're just going to be doing the odd numbered problems. So we'll be going 1, then 3, then 5, and so on. So we're starting, though, with question 1. Carrie has started to draw a cat. That's a great thing to do in your free time. Here's a cat. She added more to her drawing using her black pen, and which of the following figures can be possibly her finished drawing? Okay, so I see that, this has this kind of ears and this kind of nose, and that's pretty much all we know about it. But if we look at the other answer choices, some of them don't have the same kind of ears or nose. Like A seems to have a pretty weird, different looking nose thing, so probably isn't going to be A, because, we can't get that from starting with this normal triangle. It seems to be something different. And, well, B looks like it would work, so I'll go on to C. C, I have the right kind of nose, but the ears look different, so I think that can't be right. Then for D, it looks like oh yeah, the triangle's the wrong way around, so the nose is actually backwards, so that can't be right either. Then for E, we have a circular nose, and oh, that doesn't look good to me, so get rid of E. It looks like B works because the nose and the ears are, in fact, the same, and so this looks to be our answer, but is it correct?
Well, let's take a look. It is amazing.
Yay!
That's wonderful.
Awesome.
This is great. So for those of you guys who really like spot the difference puzzles, this problem is perfect for you guys. Because what Eli did, he looked at all the different answer choices and spotted the differences. So yeah, this is a really cool question. I think you guys did really awesome. Alrighty, let's move on to problem number 3. Okay, awesome. So we typically do like alternating questions, so odd numbers. So for question number 3, we have a digital clock in 24-hour mode, and it shows the time 2019. So if you're in the US, this is what we call military time. So this would actually be like 8:19 p.m. And we're trying to find out what will the clock show the next time it uses the same digits. So let's go ahead, take a look at some of these answer choices. If we start off with 0921, I mean, all the digits are used, but think about this. This is in the morning, so this is AM. Remember, we said that this was PM. So this may not be the closest time. Let's keep this in the books. I mean, it could be a potential answer, but we don't know just yet. Now, let's look at 2091. Okay, 91 is definitely not a possible minute, so I know that B is incorrect. I can never have 91 minutes. Now, if I look at 2109, I mean, that looks okay. This is going to be 9:09 p.m. really. And that seems to be pretty close after 2019. It's certainly closer than 9:21 a.m. So I'm actually going to eliminate A and keep C. And then if I look at D, 9:12, it's the same thing as 9:21. They're both way after 9:09 p.m. So let's go ahead and eliminate D as well. And then finally with E, this is again going to be 2:19 a.m., which is much after 9:09 p.m. So let's go ahead and eliminate this. And our correct answer is C, like so many of you guys are saying in the chat. That's the answer that I found and the answer that you guys found. So let's make sure that Math Kangaroo agrees with us and see if the answer is actually C.
Looks like it is on my screen at least. So great job, Sam. We got to the right time, but now it's time for question number 5. Okay, the sum of the opposite sides of the die are always 7. Okay, I didn't read the question, but I know what it's saying. Which of the following could be an ordinary die? Okay, so this is interesting. It means that, like, if I have a 1 on the top, then I need to have a 6 on the bottom, or a 2 and then a 5, or 3 and 4, that kind of thing. But what's interesting about something like A is I see the 2 and the 5 are next to each other. So that means that, this 5 can't be down here, which means that I couldn't have these add to 7. And so that won't work. And I can kind of just go along every time I see 2 that add to 7 that aren't on opposite sides of each other, I know that can't work. So for B, that's true as well because 4 and 3 are here. Again, 4 and 3 for C. And then for D, 1 and 6 look like they're next to each other as well. But then for E, 2 and 6 don't work, 6 and 4 don't work, and 4 and 2 don't work. So that means that all the other opposites are able to be adding to 7. And so it looks like, as so many E's I'm seeing in the chat are, it looks like our answer is E. And are we correct?
You guys are correct. Amazing. Great job, Eli, with that explanation. I think that really covered really well, like the idea that opposite sides are summing up to 7. So let's look at the sides visible to us and see if that condition is satisfied. So amazing job. Perfect. All right, let's go on to question number 7. All right, so we've got Laura, and Laura wants to color 1 2x2 square in the figure below. So we want to find out how many possibilities there are. So we want to figure out how many different ways Laura can color a 2x2 square. All right, I think the easiest way to do this is honestly to just like count. Let's count some 2x2 squares. So I'm going to outline mine in teal, some in teal. So the first ones I see are the ones in the corners over here, really. So I see 4 in the corners. And so let's write that in teal. So I see 4 in the corners. Now I also see like a 3x3 central square. So here's oh, I meant to change colors. Okay, there we go. Let's have yellow now. All right, so we have a square in the center. That's going to be 3x3. And so if I kind of blow up this 3x3 square over here, oh, that edge is missing. Okay, you guys can't see that fully. All right, let's do like a little over here. Okay, so in this 3x3 square, I need to find out how many possibilities I can color 2x2. So, for example, I can color this 2x2 in the top left corner. I can also color the 2x2 in the top right, and in the bottom left, and in the bottom right. So that means there's 4 2x2 squares in the middle 3x3 square. So in total, I see 4 plus 4 equals 8 2x2 squares. Okay, and it seems like most of you guys are saying 8 as well, and I think Eli has already went ahead and circled it. So let's go ahead and see, is 8 actually correct? And it is. Perfect! You
Wow.
are so great already. Oh my gosh, this is amazing.
So that was all about counting squares. Let's see what our next question. Question 9 is about kangaroos. This is Math Kangaroo. That makes sense. The sum of the ages of a group of kangaroos is 36 years. In 2 years, the sum of all of their ages will be 60 years. So how many kangaroos are in this group? Well, this is kind of cool. Okay, let's say I have Alfred is a kangaroo. I have George. Okay, this is going to take too long. But I have a bunch of kangaroos. I don't know how many there are. Let's say that there's some variable number of them. Let's say there's n of them. And I know that if I sum all their ages up, I get 36. Well, in 2 years, they're all going to grow, 2 years older. So it's like Alfred plus 2 years, George plus 2 years, plus 2, all the way down. And after I do all of these adding 2's, I get 60. But let's think about, like, how many 2's did I add? I added 2 to Alfred, 2 to George, and 2 to all of these other kangaroos. N of them, in fact. So 2 times n is what I added. So if I look, how much did I add from 36 to 60? Well, that's just 60 minus 36, which of course is 24. So I know that I added 2n, so 2n is 24. Now I can just divide by 2, and that means that n equals 12. And that looks like option B to me. So I see a lot of people saying B in the chat. Are we all correct again?
You guys are. Look at this amazing streak we're setting already. Wow, I'm so impressed. Alrighty, let's take a look at question number 11. Okay, so we've got a 3-digit number and an awesome diagram while we're at it. And we're writing this 3-digit number on 3 pieces of paper. So 2 of the digits are covered, and the sum of the 3 numbers, it is 826. And we want to find the sum of the 2 covered digits. Okay, so I think this diagram is trying to help us out. So let's take a look at this diagram. And basically what I see 243 plus 1 something. I'm going to represent the something with a dash. I know some people like to use variables, but I feel like if I use a variable, I'll think I'm multiplying. So I'm going to use a dash. And then for our third number, we have something and 2 and a 6. And so we know this sums up to 826. So if I see 3 plus 7 plus 6, that's 16. So I see where the 6 comes from, but I have to carry a 1. So then I have 1 plus 4 plus my dash number plus 2 is equal to 2? That doesn't make sense, right? How can 5 plus 2 plus something else equal 2? So that tells me there must be a carry. I can't just sum up to 2. I have to sum up to 12. So let's take a look. If I have 12, then I have 1 plus 4 plus my dash plus 2 is equal to 12. So that means my dash number is actually just going to be 12 minus 1 minus 4 minus 2, which is going to be 5. So that first middle digit of the second number is 5. And actually, let me write that in a different color so that it stands out a little bit. Let's do a neon green. And then similarly, we do the same thing for the front digit. So remember, we're carrying a 1 again. So this time, I don't have any other carries, because if I did, I would have a 4th digit. But instead, I just have this 8. So then I know that 1 plus 2 plus 1 plus my dash is equal to 8. So my dash number has to be 4. So I get 5 plus 4, the sum of my 2 missing digits, which is 9. All right, let's check that out.
Looking good to me. And indeed, our answer is C, or 9. And oh, that's a lot of C's from Tanu there. looks like we're in agreement. Okay,
Amazing.
on to question number 13. Pia is playing with a folding yardstick made of 10 parts. Oh, this is interesting. So like each of these can kind of swivel around. Which of the following figures cannot be formed with this folding yardstick? Okay, I think this is going to take some visualization skills. So let's make it a little bit larger. Okay, so I'm thinking like in order to make this kind of thing, we would need to maybe start over here. Oh yeah, I think the way that we can think about this is like, how do we make it all with one line? Can we just draw this line to make the diagram? And then that will tell us whether or not this can be made with these. And I guess one thing we probably should do first is, make sure that actually there's 10 segments in each of these, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Obviously, if there's more than 10 segments, then this can't be made. But you can go through and just count. I'm pretty sure each of these all have 10. So we're not going to get off that easy. Unfortunately, we're going to have to do some more interesting things. So let's see what more interesting things we can do. I think, yeah, you can kind of just trace it along, right? So for the first one, if I start at this corner, I don't think it really matters where I start. You can kind of just go along and then make a little path here. And then, oh, maybe I do have to be careful about this because, once I get to this, I can't trace back my steps. Okay. But I feel like this should be possible. I don't know. Okay. So we can't, make a loop, because if we made a loop, then we'd have to go backwards, and that wouldn't make sense. Just thinking, what do you do when you get to this middle thing? Because you have to go in multiple different directions. So Yeah, I'll figure it out. Maybe let's move on to a different one first, and then we'll come back to that one. Maybe that one can't be done. I don't know. Okay, so for this one, I mean, I can just go along and make my loop like this, just go kind of place by place. And so I know that that's definitely possible. For this one, I think, does it matter where I start? I don't know. No, I think this is fine. You can go like here, and then here, and then here, and then go over there, and then back, and then around, and then back. You know, if I draw this right, this way, this way, this way, this way. And I think that completes it, right? Because you just start here, 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 here. And here is very descriptive. I know. You can tell exactly where I'm going just from my words. Okay. Then onto this one. I think you can... So you just have to be careful that you're not backtracking, right? So let's see. Because then I would have to go backwards, so I can't do that. No, it doesn't work either. Let me think. Because now okay, well, we can move on to the last one, but I'm feeling not very good about that one. So let's see, this going here, here. Ah, there we go. I just have to start in the middle. Okay, there we go. So start here and here, go down, 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 up, and then up, left, left, and down. So that one works too. Okay, we're not doing too badly. And let's see, am I ready to tackle the first one? I haven't been figuring it out in this time. Let's see, make this loop. Oh yeah, there we go. I don't know why I didn't see this before. Let's start at the bottom thing here, go up, and then go right, down, and left. Then go left, up, right, down, and left. And there you go. You can make that one too. And so we're finally left with this one. My guess is this will be the answer. But let's just try and see maybe why it can't be done. So, if I start somewhere, I'm going to have to go along. But at some point, I have to cross one of these. And because there's 4 of these, at some point I'll have to cross one of them, and then 2 of these will already be done. And so I can't kind of go anywhere once I'm there. I don't know exactly how to illustrate this. I mean, Sam, do you have a better way of explaining it?
Honestly, I don't know, Eli. I think the way you did it is probably the way I would have done it as well. And this is a difficult question. I do see a lot of people saying that in the chat, because it does really involve a lot of visualization. So, Eli, I really think the way you did it is honestly the way to go. It was superb. And the way you found all the paths and everything, totally agree with that. So I think this is probably our best bet. But let's take a look. Is it C? And
Looks
it
like it
is
is.
amazing. Wow. What a great way to tackle that really difficult question, honestly. That was so cool. Amazing. Okay. Let's go ahead and take a look at question number 15. All right. So we now have a big triangle oh, that's weird. I don't know why it's showing up on my screen like that. Okay, anyways, we have a big triangle divided into equilateral triangles as shown in the figure. And the side of the small gray triangle is 1 meter. So we want to find the perimeter of the big triangle. Okay, after the question that Eli did, I'm feeling kind of lucky with this question because this is something I know how to do. Alrighty, so let's take a look at this. We first have the side of a small gray triangle. And we know that it's equilateral, so all the sides are the same. So we're told that the side length is 1, so I can go ahead and say the rest of these are 1. But if I kind of look a little closer, this is kind of interesting because I see some different side lengths, some different shapes, triangles in here. So what I'm going to do is I'm going to see if I can get any triangles that I can already know the side lengths for. So what I mean by that is I'm going to draw a little line. I'm going to draw a little line. And I'm going to draw some more lines over here. And I'm going to draw a line over here and over here. Oh, that's not a good line. Here, let's do one here and one here and one there. Okay, lots of lines. And these lines, oh wow, okay, that's weird. Okay, you guys totally cannot see what I'm drawing. All right, let's see if I can. Okay, there we go. Hopefully this is a little clear. Okay, so what I was trying to say is let's draw some lines here and here and here and here and here and here and here. Okay, perfect. So the idea is that these are all other equilateral triangles, and I already know that all of these, I know all of these triangles are going to be similar to this gray triangle over here, which I colored in yellow. So that means all the side lengths are also the same. So that means have a side length of 1, 1, 1, and 1 down here. So that's going to be a total side length 5. And we're told this is a big equilateral triangle, so we don't even have to find out the lengths of these other sides. So we can just go ahead and say that our final perimeter is 5 times 3, which is equal to 15, which should be our final answer of A. Alrighty, let's take a look. And
All
that
right,
is
it looks like that is right. 15 meters, a very large triangle that we're dealing with. Imagine a triangle 15 meters across. Oh, that would be interesting. Be really nice to have such a large equilateral triangle. Maybe you'll see them on bridges or something. But yeah, a little bit easier than the weird hinge question we were dealing with before. But now we'll see if question number 17 can challenge us as well. Okay. With blocks of dimension 1 centimeter by 1 centimeter by 2 centimeter, you can build towers like this. How high is a tower that is built in the same way using 28 blocks? Okay, so it's like this is the method for making the towers, and we're just using 28 of them. Okay, so let's see. I guess we should just see how many blocks we're using in each of them, right? So this one, we're using 3, and then it's like 3 plus 2 plus 1. Oh, that's interesting. This is 2 plus 1, 3 plus 2 plus 1, which is 6. Then 4 plus 3 plus 2 plus 1. Maybe you're seeing the pattern now. 4 plus 6, so 10. And then 5 plus 4 plus 3 plus 2 plus 1, so 5 plus 10, or 15. Okay, well, now it looks like the next one will just have an extra 6 on the bottom. So I'll just add 6, get to 21. And then the next one I'll be adding 7, and that it looks like 28 to me. So that's pretty cool. We have our 28 block tower. We know that we just have to go 2 more down the line. And we know that it's going to be like 7 on the bottom, then 6, then 5, then 4, and so on from there. So let's give ourselves a little bit more space. So we know that this is 2 by 1, right? So we can kind of draw some things out. We know that this is going to be all the way down and 7 of them. And then we know that there's going to be these other ones that are like this way, and there are 6 of them. But it doesn't really matter what's going on, right? Because we know that this is 2, and that this is 1, and that it'll be 2 next, and then 1, and then so on like that, right? And there's going to be 7 levels. And we just know that it starts at 2 and alternates 1 and 2 from there on. And all we're asked to find is how tall it is, right? Yeah, it's how high is a tower. Okay, so that just means we have to do 2 plus 1 plus 2 plus 1 plus 2 plus 1. Okay, that's 6 plus 2. And that should be how high our tower is. And that is a 1. Apparently it looks like a 2. You know, don't realize that. Okay, 2 plus 1 is 3, plus 2 is 5, then 6, 8, 9, 11. Okay, is 11 one of our answer choices? Yes, it is. Looks like B to me. I think everyone's saying D, though, so am I doing something wrong?
Eli, I am also getting B, but that's also using the exact same thing you did. So maybe we're just both wrong and these students are like super, super smart. But let's take a look. Let's take a look.
Okay.
Moment of truth.
Yeah, it was B. Okay, so you know, I'm not sure how people were getting D in the chat, but looks like my method wasn't too flawed.
I think my guess is since there were 7 levels, I think a lot of them did 7 times 2 instead of looking at the fact that, you know, some of the blocks are like horizontal, so they only add 1 centimeter to the height. So always be aware of your diagrams because that can give you some big hints. But yeah, to those of y'all that said B, great job. Okay, perfect. So let's take a look at question number 19 while we're working through these really fast. Okay, so we have Alex, Bob, and Carl, and they're going for a walk every day. So there's some weird hat wearing conditions going on here. If Alex doesn't wear a hat, then Bob wears a hat. If Bob doesn't wear a hat, then Carl wears a hat. And today, Bob is not wearing a hat, so we want to figure out who is wearing a hat. Well, we can see from the second sentence, if Bob doesn't wear a hat, then Carl wears a hat. And so since Bob is not wearing a hat, then Carl is wearing a hat. So we can say D is wrong because that says neither Alex nor Carl, and it says E is wrong because we know at least Carl is wearing a hat. We can also eliminate B because Carl isn't even mentioned in that answer. So now we're left with A and C, and we want to see, is Alex wearing a hat? Well, let's see. Our statement tells us if Alex doesn't wear a hat, then Bob is wearing the hat. But it doesn't tell us anything about what Alex is wearing if Bob doesn't wear a hat. So Alex may not be wearing a hat even if Bob doesn't wear a hat. And so that's why we can't say that Alex is also wearing a hat, which means that A is incorrect and C
Hmm.
is the only answer that makes sense. Right, Noah?
I may have to disagree with you,
Oh
Sam, here.
no!
Because I'm thinking, if Alex doesn't wear a hat, then Bob does wear a hat. So if Alex was not wearing a hat, we would know that Bob would have to be wearing a hat, but we know that Bob is not wearing a hat. So it can't be the case that Alex is not wearing a hat, because otherwise that would contradict what we know about Bob not wearing a hat. So I think that means that Alex actually must be wearing a hat, and that looks like option A to me. So not looking like
Wow,
Carl.
okay. Yeah, so this is kind of a really good example of why logic statements can be a little tricky. You have to be able to determine when the converse of a statement is true and when it's false. So yeah, thanks Eli for catching that mistake for me and showing that why A is the correct answer. So let's verify. Yeah, amazing job. Alrighty. This is awesome, guys. Wow, wonderful. All right, let's take a
Alright.
look at question number 21.
Cool. Question number 21. That's a nice number. 3 times 7, although I do see an answer of 37. I hope that's the answer. Maybe it is. We'll see. The cube shown in the figure has a positive integer written on each face. Okay, we see 3 of them. The products of the two numbers on opposite faces are the same. What is the smallest possible sum of the 6 numbers on the cube? Okay, this is interesting. So we know like 15 times the thing that's on the opposite side is equal to 10 times the thing that's on that opposite side is equal to 5 times the thing that's on that opposite side, and so on. So I think one thing that might be nice to do is just give them some names. Like I'll say the thing that's opposite the 15 is x. And so then we know that, well, 15 times x is equal to whatever's on the opposite side of 10, right? So 10 times, I don't know, whatever's opposite 10. So we can kind of just, divide by that 10. And I think that means that the question mark is x times 3 over 2. Yeah, 3x over 2. Because the 5's go away, right? So if we get rid of the 5's, this is 3x equals 2. So the question mark is 3x over 2. So that's the thing that's on the bottom here. And then if we look at the opposite of the 5 here, we know that 15 times x is equal to 5 times whatever is on that side. And we can divide by the 5 now, and so that is 3x. So there's 3x over here. And all we know about this is that they're positive integers, right? We know that 3x over 2, x, and 3x are all positive integers. So how can we do that and make it as small as possible? Well, I mean, certainly if x is on one of these things, it has to be a positive integer too. So there's not very many options if we want to make them as small as possible, right? We can just start at 1, and then 2, and then 3, and then whichever one works, first works at the smallest possible point, that'll have to be the answer. Well, does 1 work? I mean, that would be an integer, 1, and 3 times 1, that would be an integer, but then 3 times 1 over 2, 3 halves, or 1.5, I'm pretty sure that's not an integer. So I don't think 1 works, but then what about 2? I mean, if we look at 2, 2 and 6, those are both integers, and then 3 times 2 over 2? Well, the 2's go away, and so we're just left with 3. And so I think when x equals 2, this ends up being 2 on this side. 3 times 2 over 2 is 3, and then 6. And if we add these all together, we get, 3 plus 2 is 5, and that makes 10, 20, 26, 31, 41. Okay, so not 37, very sadly, but it looks like our answer is 41. But are we correct?
And you are correct. Amazing. Okay, that's wonderful. I think that question was kind of similar to that Q's question we had before, except you weren't adding, you were multiplying. But really great job using like the logic and figuring out like what kind of numbers work. We know that odd numbers can't work because then you have a non-integer. So yeah, I think that was really great. All right, let's go ahead and take a look at question number 23. All right, so now we have a guy named Robert, and Robert makes 5 statements over here. And exactly one of these statements is false, and we want to find out which one is false. All right, so let's see. Okay, Robert has a son named Basil who has 3 sisters. All right, I can't say anything about this statement yet. I feel like it just kind of sets the scene for me. All right, then we have a daughter, Anne, who has 2 brothers. Okay, interesting. And then Anne has 2 sisters as well. Okay, I want to jump back from C and A. I want to look at their relationship because both of them mention sisters. So if Anne has 2 sisters, remember Anne is a girl, she's a daughter, so that's sister. So in total, that means there's 3 girls. Basil is a guy, a son, and so he has 3 sisters. So these statements cannot both be false. They have to be true together since only one of these statements is false. So we know that A is true and C is true. So then let's look at D. If Basil has 2 brothers, well, let's take a look. Basil may have 2 brothers. That means there are a total of 3 sons. But if there is a total of 3 sons, then Anne has 3 brothers, not 2. So there's something fishy going on between answer choices B and D. We can't say which one is wrong just yet. So let's take a look at answer choice E, which says that Robert has 5 children. So we know that A is and C is true. So let's use that to see if Robert actually does have 5 children. So we know that there are 3 girls, so 3 sisters. And let's see. We have a son, Basil. Alrighty. Basil. And that's 1 son. And then we have the daughter, Anne. Okay. Now, if there were 5 children, that means there would have to be 1 other son. So we know there would have to be 2 sons and not 4 sisters. So let's say there's 2 sons. If there are 2 sons, then Anne would have 2 brothers. That checks out, not 3 brothers. If there were actually 3 brothers, then they would have 5 children, but we know that E has to be correct. So is B the one that is, or is D the one that is false? What do you think, Eli?
Yeah, that sounds good to me, right? Because we know that A and C have to be true together, and then if D were true, then B would be false, but E is, consistent with B. So I think the only one that's really the odd one out here is option D. And so, let's see. Is it D? It is. Fantastic
Amazing.
job, everyone.
I feel like I've redeemed myself now that I got that question. Amazing.
Another logic question for you. Yeah, it
Oh,
seems to
yeah.
be the turn of the dice for you. But let's see, is it going to be some more logic now? Looks to be something a little bit different. We have, for question number 25, a cardboard thing folded into a 2x1x1 box. And which of the pictures below does not show this box? Okay, so these always hurt my brain in terms of, how they're constructed. I think it's like you fold this thing over, and then you fold this over, and then you fold this one over, and then this over, and it's just really weird. But the only thing that I think you really have to keep in mind for these kinds of things is that if they're adjacent, in the folding diagram, then they're going to be adjacent in, the ultimate box, because all you're doing is folding over. You're not, cutting anything. So hopefully that'll be enough to answer this question. I don't know if we'll have to do some other, geometric reasoning in our minds. But hopefully we can at least get rid of some answer choices using this. Okay, so one thing here I see, is there anything I can immediately get rid of? I don't know. It's always so hard to visualize these things. It's just, this seems fine to have 2, white things. I don't know what, this is unshaded, this is shaded, and this is just white shaded, I don't know. These all have those next to each other. I think that's fine, because there's the 2 next to each other here. So my guess is this is one of the bases of the box. And so that happens in A and B, that's okay. Yeah, what else is there? Oh, okay, I finally see how this is actually constructed. It's like, you have this as the base of your box here. And then you're gonna fold this over, so that this is now a side, the gray and then the unshaded. And so that'll be one of the sides, and then you flip this over to be the top, the white and then the shaded. So I know that it's a little bit different in each of these, because for some reason they didn't keep this as the bottom, but I'm thinking of this as the bottom. So you just have to kind of adjust to that. So if this is the bottom, then actually this 2 shades on top, I think, are fine because this will be put up like this, and this will be shaded over, and this will be up like this, and that'll be over. So actually, this A looks fine to me. I'm going to say, oh, one of the pictures does not show this box. Okay, so that means that A is not the answer. Okay, good, good. For B, let's see. We have the 2 on the bottom, and then this is going to be over here, and this will be over here and here. So I don't feel like B is possible, because how can you ever have 2 unshaded things next to each other in this diagram if you just imagine it in your mind? Because like this is going to be on this side of the box, this one over here, and then this will be on this side of the box, and this will be on this side of the box. They'll be adjacent this way, and then this will be on the other side, but they'll never be on top next to each other like this. So I don't think B is possible. So I think that means that B is the answer. We can go through the other ones. Requires some more reasoning. I seem to be getting a lot of these ones that require some like geometric thinking. Okay, for option C, this looks like now the top of the box. If you remember, you're folding this over and then folding this over. So these two are going to be like what you're looking on when you look at the box head on. That looks fine to me. And then if you are doing that, I think this is also fine because you're going to have this. Yeah, because this will be the thing that you're looking at over here. Like these two on top, the shaded and then the unshaded, are these two. So that's fine. And then this unshaded thing over here is either this one or this one. I can't really tell. I don't remember which direction you're looking at it that from, but one of these. But either way, they're both on the side. So this is fine. So that means C is also fine, which means it's not the right answer. And then for D, now this is on the top, and you're looking at this thing over here, and then it's kind of the same as before, so that's fine. And then for E, these two shaded things are next to each other. I think that comes from this and this one, because when you're folding this over, this comes over here, and this is down there. So that looks fine, and this comes from the top of the box. I think that's fine. I don't know, this is really hard to visualize, but I'm going to say that that's also fine. So I'm going to say the answer is B. I'm not feeling totally confident, but I'm seeing some agreement. So let's see. Is the answer B?
And it absolutely is. Way to go, Eli. I mean, honestly, like the way you explained the problem, the way you did the visualizations, I think that was just wonderful. So amazing job. Thank you so much. Alrighty, let's look at question number 27. Okay, so we've got some cans. Cool. And we have Jete and Willie. I don't know if I said those names right, but it's fine. I think those are cool names. And they're throwing balls at 2 pyramids of 15 cans. So Jete knocks down 6 cans with a total of 25 points, and Willie knocks down 4 cans. And we want to find out how many points does Willie score. So it seems like, okay, so the stacks are identical, but we don't know like which cans go where. All right, so let's go ahead and show how many cans there are. So it seems like there should be 1, 2, 3, I think. 3 and then 5. Wait, that's not 15. Hold on. I think there's a can at the top, like up here, and then there's like a can over here. So that'll be 2, and then there's like a can over here, and then there's like 2 cans over here, and then 1 can down here. I think that's what it looks like. So that means Jete knocks down 1, 2, 3, 4, 5, 6. 6 cans, I think. Is that right? Yeah, 6 cans. Okay. And then Willie knocks down 1, 2, 3, 4 cans, I think. 4 cans. You know what? I could have literally just counted how many cans are on the screen and subtracted from 15, because we know that's how many there are in total. But anyways, that moment has passed. So since the cans are identical, we can say that they also have the same numbers. So for example, I don't know what's at the top just yet, so I'm going to leave that number missing. But for Willie, I know that one of the cans, the can on the left for the second row that he has a value of 9, because that's what Jete's has. I also know that this one is going to be 4, so the one on the third row to the left, and then the one on the fourth row to the left is going to be 8. But I still need to figure out what's at the top, and to figure that out, I have to fill out Jete's cans. So I know for the first, starting with the bottom row, the very last row in the middle, we know that she has a 3 down here, and then going up to the second row, we have kind of like an 8 on the left and then a 2 on the right. And then going up to the third row on the very right, we have a 3. And then on the fourth row, we have a 4. So adding up those known values, 4 plus 3 is 7, plus 8 is 15, plus 2 is 17, plus 3 is 20. And since she scored a total of 25 points, that top can has to have a value of 5. So Willie's also has the value of 5, and if we add that up, 5 plus 9 is 14, plus 4 is 18, plus 8 is 26. So Willie has a score of 26, and I think he won the game. But let's see. Let's see if Willie's score is correct.
Yeah, it looks like it is. Very impressive of, oh wait, what was this person's name? Willie, to win the game by 1 point, even though Willie only had 4 cans compared to Jitay's 6 cans. Very impressive, strategical, tossing of the balls to hit the cans. I think, Jitay was just going for as many cans as possible, didn't even look at their dollar values, but Willie had the strategy. Okay, question number 29. I think this is actually the last one that we'll be doing, so we might end a little bit early. Linus builds a 4x4x4 cube using 32 white and 32 black 1x1x1 cubes. Makes sense because 4 cubed is 64, so indeed 32 plus 32 is 64. He arranges the cube so that as much of the surface of his large cube as possible is white. What fraction of the surface of his cube is white? Okay, this is an interesting question. I think kind of all we really have to do is find the surface area of a 4x4x4 cube and then use as many white cubes as possible to fill that surface area and then see how many black cubes we end up needing to use. So, okay. Well, let's see. I mean, we can start off. A 4x4x4 cube just has, 6 4x4 faces like this. We do have to be a bit careful though, because if we use a white cube on the edge, that'll be used twice. Do you see what I mean? Because it's like a corner, and same thing, or like an edge, and then on a corner it'll actually be used 3 times. So yeah, this requires some thinking here. So we can kind of, I guess, make it a little bit easier on ourselves by maybe splitting up the counting. We can start with the ones that will only be used once, like the ones that are on the inside here, and that's actually just a 2x2, because you can imagine, if I fill out the rest of these, there's going to be all these other things down here. Or is that? Yeah, that's right. Because this is a 4x4. All of these are like edges, but then in here is just this 2x2 little square that's only being used once. So on each of those faces, there's 6 faces of the cube, we have those 4 little squares being used. So 6 times 4 is 24. So that's how many little cubes we have in the middle. So I'll say middle cubes. I don't know. Maybe I'll call them interior or something. But 6 times 4 is fine. Okay. And then the next things we have are these edge ones. So I won't count the corner ones. I'll count the edge ones. And we have these 2, like this, these 2, and these 2, right? So in total, that would be 8. Because it's just 2 times 4. And then 8, and then there's... Oh, yeah, but then I have to be careful because it's the double counting and everything, right? Because each of these is being counted twice, right? Because they're also happening over here. So what you can do is just kind of say 8 times 6, but each of these is being counted twice, so we divide by 2. We're double counting each of them. Maybe there's a less complicated way of doing this, but this works for me. So that gives us 24. And now we have the corners, and you can kind of just remember probably that there's only 12 corners on or is it 8? How many corners are there in a cube? There's 8 corners, 8. Right? Yeah, I don't know why I thought it was 12. It's 12 edges, okay. So 8 corners on a cube, right? You can think 1, 2, 3, 4, 5, 6, 7, 8. Just to illustrate the method, you can also do it the other way, because there's 4 per face. So 4 times 6, but each one's being triple counted, so divide by 3. Anyway, it's just kind of cool, it works, right? You get 8. So 8 of the corners. Okay, so that's all done. In order to use as much white as possible, to get as much white on the surface as possible, we'll be wanting to use those corners and those edges, right? Because of the fact that they're used on multiple faces at once. And so it looks pretty nice with what happens here, right? Because 24 plus your 8 is exactly your 32, is that right? Yeah, that's right. So that means that all we have to do is use the white cubes for the edges and the corners, and then we use the other 24 on like that are just on the sides here for the black cubes, and then the rest of the black cubes will be on the inside, but they don't really matter because we're just looking at the surface. Okay, so now we actually have to find the fraction of the surface that is white. Cool. Okay, so if on each of our little faces we have, I'll try to redraw it again, something like this. We have the four in the middle are going to be black, right? So those are going to be black, but everything else is going to be white. So these four, these four, these four, these four. And how many of those are there? Well, I guess one way you could say is like this is 4 by 4, so 16 total, and then minus the 4 on the inside that are black is 12. So on each face, there's 12 white to a total of 16. And, well, I mean, you have 6 faces. It's still the same ratio on each face. So I think this is just the same ratio as the total surface of the cube that is white to black. So it's just 12 over 16. You get rid of the 4s, and you're left with 3 over 4. And so I think, after all that work, the answer is D. I really hope so. Okay.
And it is D. Oh my gosh. Wait, a great way to end this last question, Eli. I think that was amazing. I think you made a lot of smart choices in there, like choosing how to count all the cubes, choosing which cubes to include, and also like that final step where instead of calculating all of like the total surface area, you just looked at one face. So I think there was a lot of amazing like strategy going on in that question. So thank you, Eli, for solving that very last question for us. And that concludes this live solve. But before you guys all leave, we want to invite back Mr. Kranjikar to end with a couple of closing sentiments. So, Mr. Kranjikar?
Hey, thank you, Sam, and thanks, Eli. What a great session. And to be honest, I could see that there are quite a few questions which are even difficult for the grown-ups. I'm sure there are some parents attending this session along with their kids, and I was just going through the roster. It's great to see 100 plus participants already here. Yeah, one thing I can say to all the participants is you might feel overwhelmed with some of the questions because we want it to be challenging because we know for certain schools, certain school districts, and throughout certain states, the syllabus is not that difficult and people feel they're doing much better. But then when you compare with this, you realize, oh, this is very tough. So try to challenge yourself so that you start getting better and better and better so that you would be competing against top-notch players and even participating in mathematics Olympiads. And in fact, we are running another competition pretty soon, mainly for the high grade students. And I'm also working on a project specifically with some of the my coworkers and some of the directors to see if we could do more competitions like this. Because right now, Math Kangaroo is doing only one competition per year, and I mean just one day, and people preparing for a couple of months, and then they forget until the registration starts a few months later. So just to give you a hint, start finding the best mathematical student from your class and start pairing with them because the next competition we are thinking of is going to be a partners competition so that you can form a team and solve the questions together. So start preparing on that front and be the best kangaroo. Maybe that would explain why it says kangaroo, the thing I explained in the beginning of the session. We started with Australia, so that's how the word kangaroo comes for this competition. And in the beginning, I talked there are 55,000 plus participants joined in only USA, but we do conduct this exam in several countries. And over 6 million plus participants have taken this exam so far, and we are looking to grow this number further. So, thank you very much, all the kangaroos. Start preparing for the next year session as well as start finding the good partners for your next teamwork. And thank you, Sam, and thanks, Eli, for great explanation, great session. And I could see the way you guys were explaining. It's really fascinating. Thank you very much.
Amazing. Thank you so much, Mr. Kranjikar, for that sneak peek at next year's competition and also for the kind words. We are so excited that you all joined us tonight. I'm sure Eli and I both had a lot of fun. You guys are such talented students, and we hope you keep participating in Math Kangaroo and lots of other competitions because there's so much to solve out there. With that, thank you so much for joining us tonight. Eli, if you have anything to add, please go ahead.
Well, no, just thanks everyone for being here. It was our pleasure to solve some problems, and hopefully you enjoyed watching us solve them as well. And thank you to Mr. Karanjkar for giving us some more information and giving us a hint as to how to prepare for the next competition.
Awesome. All right. Thank you all so much for joining us. And finally, have a great day, night, morning, afternoon. See you all hopefully in the future. Thank you, everyone.